Words, they get golly hard when they jumble, jumping over hurdles, slowing verbs like a turtle, murking fool like Squirtle and Kate Rule, cold-blooded with this rhyme scheme, I'm a boss.
This is That Got Me Thinking, and I'm Ellie Newman. This week, I've been thinking about science, patience, persistence, and synchronicity. I've been thinking about purpose, creativity, and expansion. I've been thinking about black holes and radio astronomy, but mostly I've been thinking about abstract mathematics and the bright light of perceptible reality. My guest today is Heino Falke. He is an award-winning astrophysicist, a visionary, a dreamer, and a master collaborator. He, along with an international team of astronomers, technicians, imagery experts, data analysts, scientists of all ilk, and some amazing chefs, took a photo and captured and created the first image of a black hole. Falke joins us today to discuss his recent book, Light in the Darkness, Black Holes, the Universe, and Us. Welcome, Dr. Falke, and thank you so much for joining us on That Got Me Thinking.
Hello, thank you for having me.
So I want to start with the question asked by Martin Rees, a legendary British astronomer who was in one of your presentations, and he was the first to make the idea of black holes respectable, and we'll talk a little bit about later why they weren't at first and how they are now and how the picture helped. His question was, what are we actually seeing in the image, the event horizon, its shadow?
Yeah, that's a very good question, because what is so special about black holes is that you in principle cannot see them, because what really characterizes a black hole is its darkness, the fact that it swallows everything. It doesn't return anything. So in that sense, they should be the darkest objects in the universe, where light disappears, all information disappears, and there's no way to see them. Yet we can see them as, we see a shadow of a person, where we don't see the person, him or herself, we only see the shadow. We can see the shadow of the black hole, the light that disappears in the event horizon. If you radiate light at a black hole, you will see a ring of light surrounding the black hole. It will be bent around by the force of gravity. It will go in circles, the light. So if you'd be close to a black hole, you would look forward, you would see your back, actually. And if you look into the horizon, the event horizon itself, you'll see, so to speak, eternal darkness, the darkest surface in the universe, or it's not a surface, the darkest place in the universe. And that's what we're seeing. We're seeing a ring of light, a ring of fire, you could say, and in the middle we see a dark patch. And that's where, the light is disappearing into the black hole.
It's interesting as you describe it that way, because I'm thinking, I'm thinking of how you guys came up with the name, the shadow, which is fabulous. And I'm also thinking about it, when you were talking about a person's shadow, and I'm thinking you don't see the heat that's emitted from the body, or the radiation from the body, or an aura, if you're metaphysical, around a person's shadow, right? It's only around the person. So that's an interesting distinction as far as this shadow that we're seeing actually has a huge energetic surrounding it.
And that's because black holes attract, right? They're the most attractive object in the universe. And, when matter falls towards black holes, it will be sped up to almost the speed of light. It will be turbulent. It will go around the black hole before it disappears, and it will heat up. It will start radiating. It will have hundreds of billions degrees Celsius in temperature. I don't know what that is in Fahrenheit, unfortunately.
It's a lot.
It's a lot, it will, it's equally a lot of radiation. And so, black holes are at the same time the brightest places in the universe as they are the darkest places. And so darkness and light exist next to each other in perfect harmony, you could say. And but the real nature, but I think that's why the shadow is a good term that we in our publication like 20 years ago, we thought about how do we call that thing that we see? We don't see the black hole. We cannot see a black hole. We only see, we see its shadow, and that's how it came up. And black holes hide behind their shadow. You can't see their personality. If you see a person's shadow, you can see a few things, right? But you don't learn everything about that person. You're missing a lot of information, and the same is true for black holes. And they are the objects that only allow you to see their shadow.
You said for a long time it seemed that the deep darkness of black holes would remain completely and forever hidden from our eyes. Why had that been the thought, and what changed?
Well, it took a long time to really understand the concept of black holes and what they mean. As you mentioned, they weren't respectable objects. I mean, Albert Einstein, who proposed the theory of general relativity, didn't believe they could exist. They would be out there. He thought this was just mathematics and it would not be a realistic object. But they do exist, and but you have to understand, where are they? How do they work? How could there be light in the first place? And if there is light, and you want to see the darkness, that object is going to be incredibly small on cosmological distances. So it would be impossible to see, you would think. So if someone thinking about black holes like 50 years ago, he or she would have thought, well, that's just a pie in the sky. That's far away. There's no way we'll ever see them up front and close. Yet here we are, because technology progresses, and at some point fantasy and dreams are turned into reality and actual observations and into real science.
And the culmination of your life's work thus far. So maybe I want to start with a couple things. I'm thinking about Einstein, and we'll talk about him later for sure. But how even though he didn't believe that they existed, he still thought a lot about them, right? And I want to talk about the white holes before we end the conversation for sure. But first, I want to talk about some basics. What exactly is a radio astronomer? Because I think one thing you said in the book was the size of the black hole would be like a quarter of a mustard seed at best. And so
at the distance of Europe seen from the US.
Yeah. So how are we able to even pinpoint it? And what is the role of the radio astronomer in doing that?
It's an interesting question, because until I would say the 50s, there were astronomers, and astronomers would look through a telescope, which was something with mirrors or with lenses, and they would use their eyes, or would use a photo that would take pictures with. And then suddenly, after World War II, astronomers were starting to use radio antennas to measure and detect radio emission from the cosmos. And what we know is that radio emission is actually like optical light, like the light we see. It just has a different frequency. It's the same thing. It just has a different color, a color that we cannot see with our bare eyes, but we can measure them with antennas. And so in that time, people suddenly started to call themselves radio astronomers, because they were using radio waves, not the optical wave that we see. And suddenly there were optical telescopes, because telescopes used to be just one thing, right? But now you had radio and optical, and today we have X-rays, we have gamma rays, we have near-infrared, we have far-infrared. We have all kinds of colors that weren't around for astronomers to use in the last 2,000 years. We used our bare eyes to look at the skies and lenses, and now we use the entire electromagnetic spectrum, and we see sort of a much richer universe suddenly. We see so many more colors nowadays. I was comparing this, I think, to a piano. Which has different, octaves, and we can play, and you would play with just one octave on a piano. And now we have a piano which is 12 meters wide, right, or 12 yards or whatever. So many frequencies and sounds and that we cover these days. But then, you have to have radio antennas, big dishes like a satellite dish you may have on your roof, just much bigger, and then you need to have a resolution that gives you the resolution to see a black hole. It's this mustard seed in Europe seen from New York, and that requires a telescope the size of the Earth, a world-sized telescope.
And how does it? The other element, just of the technical aspect. So before we start talking about the rest of it, is how then do you barrel through all of what's in between Europe and America when you're looking at the mustard seed. Like one thing you mentioned was that you're using radio emission of distant black holes as cosmic landmarks. So you're mapping the whole universe, the galaxy and then the universe. But how are you filtering out what's between you in Chile and the black hole that you're looking at?
Well, of course, we are looking into space, and space is largely empty. It's full of stars and it's full of black holes. So if you make a picture of the universe with a radio telescope, you would see it. You wouldn't see individual stars. What you would see were actually black holes, because this will dominate your view. You would see blobs of gas. You would see streaks of plasma streams shooting out from the centers of galaxies. You would see little compact sources. So it would be an entire ecosystem out there of radio sources that you would see. A completely different universe than you would see with your naked eyes. And then, of course, you have to know which object is where, right? So, and then this radio source there, like the one we're looking at, Messier 87. Well, that's in the heart of a galaxy, and that was first seen with an optical telescope. And so you have to compare the radio picture with the optical one, identify them, and then zoom into the heart of a galaxy, and there you want to see the radio emission coming from near the black hole.
That was you say it casually, but that was one of the things that also just blew my mind when I think, how did Eratosthenes calculate the size of the Earth so long ago? And you target the emissions of a black hole billions of light years away. And you had said something about, it's simple trigonometry, which everyone in my house thought was kind of an oxymoron for those of us who don't think trigonometry is so simple. Does it make sense to you that centuries ago, people were able to figure out so much about the heavens?
That's an amazing thing that you mentioned, and that's in fact a misconception that people have often. They think, the ages in the Middle Ages, people were thinking the Earth was flat, right? And only Columbus discovered it wasn't. Well, the kings at the time would have been very stupid to give someone a ship, 3 ships, very expensive ones, to go, over the flat Earth and then fall off at the edge. No, at the time they already knew the Earth was round. It was a sphere. You can see that in some insignias of kings at the time, and indeed, an old Greek already measured the size of the Earth and actually calculated them with basic math that you learn at high school. And I'm pretty sure, I think if you go back to your high school lectures or whatever, your high school schools, you'll be able to figure out the size of the Earth as well if we do this together. Just measuring shadows again, shadows of sticks that he measured at different latitudes of the Earth. And that's amazing. With simple things, you understand a few basics of our universe. But then, if you want to really understand it, get to the bottom of it, you need better telescopes, sharper vision. And that's only been happening the last, 100 years. And it's certainly been accelerated the last 20, 30 years. Boy, what kind of pictures have we seen from the space telescope, from the ground? Beautiful pictures, in colors and structures that no generation before us was allowed to see. We saw our Earth from above, this beautiful blue pearl on a black background. That's such a pleasure and a grace, you can say, that we are allowed to see all this. No generation before us had been allowed to see that.
You had said, how astounding is it that throughout the entire universe, everything is bound together by the same processes and plays out according to the same laws. And as you're talking about what we're now being able to see out in the cosmos, I'm thinking about the parallel as to what we're able to see in the last decade or two internally, right? And how our minds work and the digital mapping and all the other kinds of brain mapping.
Oh, I sometimes have the impression.
Sorry, go ahead.
Sometimes I have the impression, actually, we by now know the cosmos better than we know ourselves, right? But because you can look into the universe, and it's much harder to look into your brain, to your
So,
mind.
what do we need to understand about light, space, gravity, and time to better understand the significance of the black hole?
It's interesting that black holes represent so many different things. They are the most extreme form of gravity, the end product of stars, the ultimate end of stars, the ultimate destruction places where everything is torn apart, where everything disappears. And yet they're some of the most simplest objects in space. Everything is reduced to how heavy a black hole is. All other information just disappears in a black hole. So they're utterly simple, and yet so exotic and complex. They twist light and space. They let time run much more slower. They almost make it look as if time comes to a standstill if you come to the edge of a black hole. And so if you think about the Big Bang and black holes, then you could think of the Big Bang being, these are the alpha and omega of the universe. The Big Bang, the beginning of space and time, and black holes are, so to speak, the end of space and time. And if we think about what space and time and gravity is, this is where we, can try to understand it or fail forever. One of the big challenges still is, what is time, for example, right? And where does this universe come from, and so forth. And this is really one of the fundamental limits of our knowledge at this moment.
You call the black holes the gates of hell, and I read that and I was like, does he believe that? Because I don't believe that you believe that. I believe you love black holes. You've been fascinated from your youth, and you've spent your entire life dedicated toward them. How are you feeling about them once now you've seen the image?
Well, they are. I mean, of course, it's not literal hell, but I think they fulfill all the things you associate with hell. They're sort of a modern mythological objects representing sort of a physical, representation of hell, where the ring of fire you have to go through. You go into the inside where you were completely lonely. You're not able to communicate with the outside world. You could actually still look and see to the outside and see what's going on, but you would not be able to tell anybody. So, you think about the big beyond, you think about death and destruction. On the other hand, it's always good to think about these things, about your own death, about your own destiny. And it has a certain fascination, of course. I mean, everything that's dangerous and it's a thriller and is fascinating. And as long as I'm not too close to them, I think it's absolutely fascinating, riveting to think about them and study them. So in that sense, I think that's not an exclusion. But it's a warning, don't get too close to black holes. It's
I'm thinking about time and time being relative. And one thing that I think for anyone listening, reading a book would not feel relative in time is that the time it takes for astronomers to oftentimes test a theory or find out new information. And I was so in awe of the ability not only to have the patience and the fortitude to continue on, but the satisfaction of just adding something, even if it was something small to the equation or to the puzzle, instead of having to only see success in figuring it all out. You waged a battle over, and you actually weren't waging the battle, but it turns out people in your community like to have a fight going, and over the battle over emissions. And it was 30 years to clarify that it was the millimeter waves emitted in the vicinity of the black holes. How did that get started, and what were the two opposing views?
Yeah, of course, when you start as a PhD student, you don't know, I'm going to take a picture of a black hole, right? You think about the big questions, and I knew black holes were interesting, and I wanted to do something with black holes. I didn't know what and where to go, but I knew I wanted to be really, close to where the action is. And but then, you have to start with little things. You have to learn how black holes work, where are the interesting questions, and you have to, try to understand them. That's what I did. And then you have to be lucky. Right? Of course, you also have to be lucky that, I was there at the right time, at the right moment, and realizing boy, this type of emission, right, comes from the edge of black holes. And if that's true, if my model, if my idea is true, then we would be able to see that black hole. And that was sort of an amazing moment, which I, in the book called the amazing grace moment, because, it's the moment where you were blind and now you can see. And that only comes after a couple of years of research where you don't know where it's leading. And suddenly you have this eureka moment. We're able to see that black hole. And that's not the end, it's just the beginning. It sets the course for the next 20 years. This is where you want to go. And you have to make detours and so forth to get there. In the end, we managed. We got there. It's something you cannot plan. But, this is how science works. You're fascinated by the questions. You are absolutely curious. You don't know where it will lead you, but you just follow your curiosity and you do what you are passionate about, thinking and researching and trying to find, a little bit of truth. And sometimes it's something that is, really big and captures the entire world by surprise. I mean, that image that we made was seen by 4.5 billion people all around the world. It was a magic moment. And this is something that doesn't happen all the time. In fact, it's a very rare event in science. And I would have been happy without it, because just following my curiosity and trying to find out.
You said what I wanted was certainty. I wanted to see black holes more than anything. That to me is the most telling thing, because you say, finally I can see. It's really the driving moment for me, the moment I live for. And I was so impressed by that throughout your writing. I was so impressed in your actions. But that intention, that to have a goal and to have curiosity and to be sort of steadfast in pursuing it, that's where the purpose and joy in life is. You also throughout the book often say, the miracle has happened. And there were so many synchronicities and miracles. And I know that some scientists, maybe even the gal that wrote the foreword in the book, might think that wasn't appropriate, but Einstein would certainly be rooting you on because he believed that everything in life was a miracle, or nothing was. And one of the things that you stumbled upon, I put in quotes the way that I see life happening, one of the synchronicities was you coming upon an article by James Bardeen, and you were reading it and you noticed that the circle was far too big. What was that aha moment?
Yeah, no, I had this idea, it might be possible this light, this radiation would come from near the event horizon. But then I was calculating how big that dark region should be, roughly. I was talking with colleagues and, it seemed too small. And as I said, you need a Earth-sized telescope to see what we now saw, which means, we connected telescopes all over the world. And if you want to see something that's even smaller, you would need a telescope that's bigger than the Earth. And that is, was completely beyond my reach in my lifetime to build a telescope, bigger than Earth. So that was clear. And so I was very frustrated for a couple of years, but it was still in the back of my mind, right? This was working, right? You had this idea and said, it's not quite working out. It's not quite working out. And I was sitting there in the library of our institute and reading through some old books. That's the advantage of books, right? You sometimes come across things that you didn't plan. I was looking at another article, actually, and I just saw this one little article, which was hardly noticed. Just a very few people had even quoted that article. A few people knew it existed. But it was doing a calculation how big a black hole would appear if it's illuminated from behind. I saw, as you said, that thing was, that what we later called the shadow was much bigger than expected. And I was thinking, says, oh yes, of course, I forgot. Black holes are like gravitational lens. They magnify themselves. This thing is 2.5 times bigger. And if that's true, if that's true what I'm seeing there, then we should be able to see the black hole with telescopes here on Earth. That should be possible. And it was such an amazing moment, as I said, to realize this, and also how stupid I was. That's in hindsight, you think that should have been obvious, right? You know how GR works, general relativity, how light is being bent, but yeah.
Yeah, but I don't think it is stupid, because you can't get past the narrative that you're carrying and the laws that you've built that around until you do, right? Like, yeah. It's not till something does spark that shift that then you can move beyond those, because prior to that, you're analyzing everything within that construct.
Absolutely. Sometimes you need someone to change your view a little bit, to give you a little new insight. And that's how creativity works. You think about something, you don't come with a solution, but then a little remark from someone, a little picture, a little drawing, a little article, like in this case, trigger something in your head, and you pull things together, you make the connection, and then suddenly something completely new comes out. Something that, in the hindsight, would have always been obvious. But at the time, nobody was making the connections, and I was fortunate enough that I made that connection at that time.
And you had these events occurring throughout the years of the project. You met a classmate by chance on the train who happened to be studying something in parallel that fit perfectly with the project that you were interested in creating. You won the Dutch Nobel Prize, the Spinoza Prize. And then further on, this one really got me, the one pulsar being detected in our galactic center that never had before, and one has not since, really sort of pushed you over the edge to success in funding your project. So let's talk a little bit about the project and what it took to get the photo taken, because there were so many elements. You had to come up with a theory, you had to do some great marketing, you had to raise some money, you had to build a team, you had to have luck with weather. What were sort of the main challenges, and what did that path look like, and how long did it take?
Well, from the first idea to the final realization, it took 25 years. And of course, it's never something that you do entirely on your own, because you're synthesizing input from other people and you're talking with each other. I think I was, one of the first who had a very clear vision to say that, this we can do with that technique. And then it's about convincing other people. It's about talking. It's, this is science. You can be right, but, others have to say, yes, you are. And then they have to give you money and they have to believe in your idea. You have to believe in your vision. And that takes a long time. And then others suddenly also have the same idea, right? Or they pick it up. And then, a race starts, actually, who is the first. And then it comes about, it's about finding the funding and so forth. And so it's a very complex process. And then building a global collaboration, which is maybe the hardest thing. We know this in this world today. Working together on a global level is not easy. And what we have in our collaboration is people from Asia, from the Americas, from Europe, a few from Africa, Latin America, of course, and different cultures, different funding streams, different egos, and they all have to get the same vision, the same idea. And it's amazing how this process works, how out of, a loose ideas, people come together. And they bring all their resources. It's not that we had just one funding source, right? We got a lot of money in Europe. You just mentioned this. There, some others brought their telescope. They brought their funding. Some of our American colleagues got some big funding. So it really is a network that grows together of sometimes competing interests, but in the end, working towards the same goal, because they're all fascinated by that idea, wanting to see that black hole.
I love the idea. I just know why it popped in my head of like everyone meeting on the Sandlot, right? And you say, okay, go home and get everything you can find and bring it, because we're going to need it. And everyone just dumps their bag of stuff that they brought and figure out how to make it work.
And people bring their own skills. In the end, the image and the way we made it, I was so impressed, because it was a new generation of very young scientists, PhD students, some of my own PhD students, some young postdocs in Harvard, MIT, but in Arizona, all around the world, working together and excelling and bringing their own skills to the table. And that's as much needed as, all the different stuff that you have, telescopes and money and software and so forth. So it really is that what you say, grabbing everything you have and then, constructing something and building it with these different, skill sets and means that we have throughout the world. And that was certainly interesting. And it was totally moving and impressed to see how, out of this chaos, suddenly, with discussion and passion, something really, really beautiful emerged and really good science in the end.
And even after you've captured the radio emissions for creating the image, you're nowhere near done. You have no idea if it's going to work. You don't know if there's no backup. So if the data gets lost in shipment, that's done. And then a huge cadre of other specialists have to step in to do all sorts of analysis and image creating. How long did that part last, and how long was it before you knew that you actually had captured what you were trying to capture?
Well, over this long time scale, it was almost fast, I would say. We did this observation in 2017. We had a few test runs before, starting in 2015, of course, before there were even Pathfinder experiments throughout this entire 20 years. But really, the real first big observational campaign was in the end, 300 scientists around the world were involved, 8 telescopes on 6 different mountains around the world. We took the data, we took 5 petabyte or 4 petabyte of data on hard drives, at all these radio telescopes, which were later brought together. And that was in 2017. And in April, sort of, around spring 2017. And then in around spring 2018, we got the data, because you have to ship them back. Some data came from South Pole. We have to analyze it. And that's where we saw the first hints that there's something really interesting, that the experiment worked. Because you only know in the end, after a year, whether all this effort, had worked. Because the data are stored on hard drives, you have to bring it together, and just only once you've done it, then you know. And so that's where we saw the first glimpse. And then, for me, it felt like it took a decade to work on the data. Yet it all happened almost within a year. So in the end, it took only 2 years to process all this data. But it was like a pressure cooker of young folks, hunting this data, tracking down every issue. There were, so many issues that can go wrong. Different telescopes have the different personalities and so forth. It was an absolutely amazing period for all of us, and a period we had to recover from, because it was absolutely exhausting.
And you had to, not only technical issues, but you had to bring back your team in Mexico because of bandits.
Well, that happened a year later. That indeed, there was some little minor war breaking out with gangs and so between secret police and some local.
Oh, that was the second time when you were trying to do it a second time.
That was a year later,
Yeah.
and then one of my students were going to the telescope. Were held at gunpoint by 6 people jumping out of a black truck with machine guns. 6 people armed, masked, and that was a very scary moment. That's when we pulled the team from the telescope. The telescope was closed for quite some time because it wasn't considered safe anymore in that region, and that was I was very nervous when I heard that. I mean, it's your PhD student going there, right? You feel responsible, and then suddenly, they're, and he comes from a region, he came from a part of Germany where you don't have any crime. It's
This was new.
I mean, a colleague of mine from Boston said, "Well, that's even much worse than anything we had here in Boston, right?" We've never seen a gun. Actually, in Germany. We don't see these things. It doesn't happen. You're not held at gunpoint, and then suddenly 6 people with machine guns jumping at you. It's just so unreal.
But it turned out you had captured what you needed to produce the image the first time around. I want to talk a little bit about light, because it plays, I think, the leading role in all of the cosmos, and it's at very different aspects than time and space, and some of which are paradoxical, that it can be a particle and a wave at the same time. Nothing can move faster than light because nothing can be less inert. Can you describe a little bit about what that means and how it's the deepest level, like that light is really, light and energy, and one of the same. They're at the deepest level, they're everything, which I think is so important, because I think it seems that it all depends on what level one is making the comparison in science when we're comparing apples and oranges or gravity and quantum physics.
Yeah, it's very interesting, and that's a very recent realization. I mean, recent in terms of the last 100 years. We always think that matter is everything and so forth, but the first thing, if you think of the book of Genesis, let there be light, is the first thing created, and if you go to the Big Bang, it's one of the first thing that's around is energy and light, and out of which matter can arise. It turns out you can turn light into matter and matter into light. That's something that, famous equation of Albert Einstein said, E is mc squared. That used to be very popular. And it also turned out that light sets the stage for space and time. It measures space and time, and that light is the only constant in this universe, in a way, the constant measure, I should say. That's something that Einstein realized. Light is a ruler, not space, not time. And space and time can change because light stays the same. And that was quite a remarkable shift of understanding our universe, that, the properties of light essentially determine the space-time structure of our universe. And so he turned things around. And also, if you think about forces, it's when you talk about quantum physics, and you hit someone on the head with a hammer, and you're essentially on the lowest level, you're exchanging virtual particles, virtual light particles, so to speak, that carry the force. So, everything to some degree is light, and that's why, light is so fundamental. The nature of light is so fundamental to everything we do.
And that's such a huge shift, and it's one that sort of was, I think, quietly accepted, and maybe not everyone even knows about it any longer, that's now considered a fact. And so when that happens in science, does it just infiltrate and shift everyone's focus a little bit once that's accepted? Once, how much can you trust what you know? And how much do then, when something like this happens, when there's a major shift that's accepted, shift the course of everyone else's study?
It's a paradigm, and it's a remarkable paradigm, remarkably successful paradigm. And it dominates the theory of relativity. And it's also, what I mentioned about light is also part of quantum physics. But quantum physics also has other elements. There is matter, right? So there are particles, which I said you can come from light and so forth. And quantum physics has its own paradigms. And so now it's interesting. We look at the world, with the tools of general relativity, and then we understand space and time in a certain way, and then we look at space, time, and information from the quantum point of view, and that sets a certain paradigm, and that has both fundamentally, radically shifted the way we view this world 100 years ago, quantum physics and general relativity. But we know both theories are, at the lowest level, not compatible with each other. There's something wrong. And so there's yet another paradigm shift that we need to make in the future, and we just don't know in which direction.
Or another piece, right? Like the third body. Yeah. Maybe we just don't have the third body yet that fits them then together.
Yeah, well, maybe it's just a bright idea that we need, or some higher picture. Because, every theory is a description of reality. It's not reality itself. It's a picture that we paint, and it helps us understanding things. And it can be tested. That's very important in science. We can measure it, and it makes predictions. But there is a certain, certainly at the edge of black holes, none of these these two theories can give a complete and full description of what's happening, because either one, they're both contradicting each other at the black hole. And that's where, some new piece, some new idea, that could be very fundamental.
Let's throw out the wave-particle dualism piece, just to put it in people's minds, because I think it's a simple one to understand when you explain it with no one ever really understands. Quote Schrodinger's cat, and I love that you say there was really no cat in the box. It was a thought experiment. I think that's really important too. But the idea about the smallest particles of matter, and that electrons can go through two doors at once unless you install a photosensor that measures their passage. So maybe just let's plant those seeds in people's minds before we move on to our final topics.
Well, there are two things. One is the duality of light, which can be either a particle or a wave, and it really depends on the question you're asking. You get a different answer. So if you're looking for a particle, you find the particle nature of light. If you're looking for a wave, you find the wave nature of light. And so that's quite interesting. It shows that our our perceptions really depend on our model and our questions sometimes. And it's important to ask the right questions. And then matter itself, we always picture the atom as, the matter that we are made of a, a proton with a big ball in the center, and then a little ball around it, which is the electron. And that's our atom. But in principle, these things are not entities like we understand them. They're just probabilities that something exists there, that they are, somewhere here, but they could be at different places at the same time. It's only when you measure them exactly that you know where they are. But if you've done that, you don't know how fast they are, for example. You can only measure one aspect of quantum particles. And so, the quantum world becomes almost, counterintuitive. It's almost impossible to understand that, to bring it to rhyme it with the universe, the world that we see around us.
At one point in the book, you say that Einstein would, if he heard this, he'd be rolling over in his grave. And I thought about that, because I thought, would he, I started thinking about, what would Einstein think? Would he have believed that his word was the last word when he left the earth? Or would he have assumed that there was going to be so much more? And what do you think, if he came back tomorrow, that he would think about all that was happening? And do you think he would still argue for the white hole?
Oh, wait, we didn't talk about the white hole.
We didn't, and I want to talk about that before we go. That bridge, I love it.
Yeah, which is the opposite of black holes. So let's come back to that. So what would Einstein think today? Well, I never met him personally, I must say. And as correct as he was in the early days, in the final days, he was just, taken over by many other scientists. Mm-hmm. So he wasn't coming up with...
I guess that's what I'm asking, though. Do you think he would have, or one in his place, because we don't know him, would have expected to have been getting it all right? Or would he just think, okay, from where we are and what we can see and what I can know and how I can think about it, this is the next piece. This is the next step on the ladder.
I think he would have been totally amazed and blown away by the fact that black holes exist, and that they work, that they're perfectly described by his theory, and that 100 years later we're using the theory and we can explain extremely well what we're seeing there. I think that just for a scientist, this is beauty. Yeah, you describe a theory which is simple, from a few simple ideas and principles. You develop the mathematics, which is hard enough. And then that mathematics stays immuted, unchanged for 100 years, and explains, in great detail, precision measurements, not just the black hole, there are pulsar measurements and other things, rotational waves, and so forth. So it's a mind-blowing success of this theory. And it could lead you to be arrogant, and I don't know how Einstein is to say, that's it, that's everything. But as a scientist, of course, you always hope that there's some new idea or some new door still. And I'm pretty sure Einstein would have started to think about that. As I said, to think about how to bring general relativity, space and time together with quantum physics, one of the big topics these days.
And how about Hawking? He saw a lot more.
Well, Hawking was working on that. He was just like many others, and he was the first one to, in a very clear way to bring these concepts together, and that led to this discovery, which is theory still, of Hawking radiation, the fact that black holes can evaporate in principle if quantum physics is true, and if what he calculated is true, and that poses one of these big problems these days, because if you have black holes evaporate, then all the information that once was in a black hole would be set free again, in contrast to what I said before. But where is it stored? How do you make sure that all the information that goes in comes out properly? Because it was all destroyed more or less in a black hole. How is that possible? And so that's what Hawking showed. The problem with Hawking is we don't have an experimental verification yet. So it is a lead, but even Hawking, let's put it that way, even Hawking didn't manage to put together this big theory of everything. The theory of space, time, and quantum physics and everything, and we're still looking for it. So it takes more than Hawking and Einstein to do this, apparently, and that's a big challenge for the young folks out there.
And maybe the good one, right? Because you say science is not an absolute method for explaining everything in and beyond the world, but rather a celebration of human creativity and curiosity. So that's perfect. You talk about light quantum in one of the last chapters, and about all about perspective, and we see things differently at different perspectives and filtered through various narratives that we hold true. And I'm thinking about that as far as and I couldn't put all the pieces together because it got late and my brain started to hurt. But my thought that when we're talking about Hawking and the idea that he was focused on information, right? And that's one focus of, if that's what's stored in the black hole, and if that's the basic element that we're focused on, versus just pure energy or pure light or something else that we haven't identified yet that can exist, right? That's connected maybe to all of those things. And it seemed like you had a very optimistic perspective in the last couple chapters about the idea that even if everything so far we understand about the black hole is true, that it wouldn't necessarily mean that it's the mass destroyer and it will be the destruction of all. Is that guiding your thoughts and your research and your work in the next few decades?
Well, I'm always a hopeful person, right? So that's throughout all my life, I've been, an optimistic person in the sense things are doable, and I'm a person of faith as well. So I think in the end I'm not scared. I'm not scared by my own death, by my own future, and I think there's an enormous creative force in this universe, and we'll go back to that creative force in the future. And so much happened in this universe. If you think about what started from the Big Bang. And nobody knows where the Big Bang came from, but so many things happened that turned gas into the particles into gas into stars and planets. Those planets suddenly had life and plants, and then had humans. We now see something like dark energy, which drives the universe apart. Something that wasn't visible in the past. So many things happened along the line of the life of the universe, that I'm quite optimistic that there's more to be discovered and more to be seen. I that's one thing I feel often, that I see a very pessimistic view of even Hawking and others were saying, this world will be destroyed and we'll just kill ourselves and blah blah blah.
I think he found comfort in that. Done what I could.
Yeah, I don't know whether that it was. I'm not sure it was comfort. Yeah. I mean, he was certainly struggling with his own demise, getting older and leaving this world, and
resolve.
I have no fun. I have no fun in thinking that if I go, this world is doomed, or the world itself is doomed. I have a hopeful perspective of this world.
And a relationship to something beyond, as you mentioned, faith. So let's, in these last few minutes, if you wouldn't mind, describing what you can of the Einstein-Rosen bridge, the white hole, the counterpart possibly to the black hole.
Yeah, that if you just use the math and you describe a black hole, then you can have the opposite, a white hole, where quite opposite. In the black hole, everything can only go in and never out again. In a white hole, everything can only go out and never in. And so it's sort of an endless source of matter and material and whatnot. A singularity, a point out of which everything evaporates, so to speak. The problem we have is that we don't have any evidence that these things exist. We have no idea how they could be made. Of black holes, we know how they could be made. But gravity, pulls everything together, and the end stage is all matter compressed into one point. It's a black hole. Creating the other thing is, we don't know how to do it. It fascinates people because theoretically you can connect a black hole and a white hole and could connect different parts of a universe. Sort of have a wormhole, but that's in a very simplistic mathematical picture. Yet it doesn't stop people from thinking about it. And if there's a theoretical possibility, maybe it's realistic. So it's something you should not discount right away. But at this point, we don't have all the ingredients you would need in physics to actually create a white hole, and we have no clear idea how they could have been made. So while they may sound like a fantastic idea and they're great for science fictions, it may be that they're not part of our physical universe. How beautiful the math is.
And are they in relation at all to the idea of multiple universes?
That thing that people talk about, whether there's just one universe or multiple universes, right? This is one of the big problems in physics that people
questions.
Yeah, how can it be that this universe works in the first place? Now, that's one of the biggest mysteries.
That's a big one. Well, and I'm just thinking now, as I said that, I'm thinking, and can we have parallel timelines within a singular universe, or do we have to have the parallel universe to be able to have parallel timelines existing? Because that's one thing Einstein believed, right? That time wasn't linear, that there were parallel timelines to some extent.
Well, there's a whole school in quantum physics which thinks that every time something happens on the quantum level, a completely new universe or a new reality emerges, which sort of separates. I am.
Yeah, and I never had thought about before. Does that mean they're in a separate universe, or are those all happening within our universes, and maybe they're all happening within the white hole? We don't know.
Yeah, but the point is, this is just to some degree, it's just blah.
Yeah.
Because there's no way at this point we could test this, right? I mean, to think that suddenly there's another universe springing out of existence. Like, I saw that on Star Trek Discovery. They had the parallel universe. It made for a good story, or better war story. It makes for an interesting story. But if there's something that's not testable,
but wasn't that the black hole initially? Wasn't that, and not to say that this one will then prove right, but that isn't the spark in that, and the idea that it wasn't respectable before to talk about the black hole because everyone was like, oh, there's no evidence, there's no way we could prove it, there's no way we could take a picture.
Well, I mean, it was a mathematical solution, and then someone like Oppenheimer showed in principle you can have a star collapse and it would give a black hole, right? So you had some reason to believe it's not completely crazy to think about it. And so it was clear that was in principle testable, right? But some of the ideas I hear about multiverses or these parallel universes come into existence are that they are still, at least even in principle, not measurable. And that makes it, a complete, source of fantasy. If you want to do science, you can think about it. It could be philosophy. It could be like some sort of faith or whatever. But it wouldn't be science anymore if you postulate something that is not measurable. And so that's what I feel sometimes about these parallel universes, right? These, you postulate different reality out there. But, if it doesn't affect you, if it's not measurable, it doesn't affect, others around you, what's reality? What is it then? So you have to be a bit careful to not get lost in parallel universes. We have to work with the universe we are living in and try to understand that one. If there's other universes out there, well, I mean, yeah, I would not exclude this forever, but you have to come with a better argument why, how to see them, how they, how to measure them, and then you can keep talking about it.
We need some math. Until then, it's fantasy. We need some math.
Absolutely, yes.
I want to just share, before we end, a statement that you made, because I feel like it's a universal statement, not just in relation to science, but in navigating our lives at any point. And you say, what's important is that everyone have their own goal to follow that suits their actual talents, and that these talents supplement those of the others in the group rather than have everyone competing against one another. And you talk about that in relation to being a grad student and managing your grad students, and then the success of taking this incredible image. So thank you. Thank you for the work. Thank you for the book. We have 1 minute left, so I'm going to just plant a question out there. It was something that I just could not wrap my mind around, and maybe you can give a little more data, and we can all end up thinking about this throughout the day and the night or wherever we're listening to the show. And you say that if the speed of light were infinite, all information in space would reach me instantaneously. What does that look like?
It would take away a certain level of freedom, because the fact that light is finite means that, what counts is what's now here with me at this moment. And I cannot predict what's going to happen to me over, a few weeks, even a few minutes or whatever, because the information from the future hasn't reached me yet. It's unpredictable. And so the fact that light is finite has many important implications in science, but it also gives us to some degree freedom. It decouples us from the rest of the universe. And that means that, how good we understand science, how well we can predict, the future is always open.
All right. Well, Heino, thank you so much for joining us. I've been speaking with Heino Falke and his new book, Light in the Darkness, Black Holes, the Universe, and Us.
Thank you.
All right. So who are you going to be rooting for now for the rest of the Cup, or are you just done watching?
Netherlands was eliminated. I'm working in the Netherlands. I'm German, so Germany is out. Maybe I root for Switzerland. They apparently did it
Okay.
yesterday. So,
All right, I'll join you.
Let's do something different.
Yeah. Okay, thank you so much. Good night.
Yeah, thank you. And have a good day. Bye-bye.
Bye-bye.